I'm pleased to see there are a few students here, not just postdocs, so welcome. You may not realize that there are a number of postdocs who are interested in this subject who are in this class. Today we seem to be roughly distributed between between the two classes. I'd like to begin by making some remarks about the importance of of an understanding of the basic ideas of high precision experiments for theorists, since at least some of the people in here are theorists or aspire to be theorists. I was a grad student at Princeton a number of years ago, and I had the opportunity to sit in on a course sit in on a research group meetings of the group of Bob Dickey. Dickey was the person who really was responsible for the discovery of the cosmic microwave background, although due to historical accident, the discovery was actually made by Penzias and Wilson. They didn't know what they had, and Dickey told them because he was in the process of looking for it, and he would find it a few months later. And Dickey was a great experimental physicist. And just by sitting in on his research group meetings, I got some sort of a feel for issues in high precision experiment. I was going into the field of general relativity. General relativity was devoid of experiments except for a few classical experiments that told you it was sort of right. This was in the early 1960s. As I went on in my career, I lived through a period of great excitement as high precision tests of general relativity became possible, and I and my research group were involved then on the theoretical side in laying theoretical foundations for understanding those experiments and proposing new experiments. Cliff Will was a grad student in that era, and he sort of took that effort over after he left. But I could never have thought about the issue of the connection of general relativity to experiment if I hadn't spent some time in Bob Dickey's group and gotten a feeling for experimental issues, and particularly in precision experiments. I think the time will come when string theorists will be doing the same thing. And let me give you an example that makes me also think that. Some years ago, maybe 10 or 12 years ago, Frank Wilczek, who's a particle theorist, came to me. He'd never thought about experiment, but he had the idea that the dark matter might be axions that were produced in the Big Bang. And he wanted to learn about how might one go about searching for axions, and he wanted some guidance. He came to me because he knew I was a theorist who had thought about high precision experiment. I was close to a guy named Berginsky, particularly, whom he was eager to learn from. But here again was the case of a theorist who had need of really understanding high precision experiment in order to think about how to test ideas that were near and dear to him. In my own case, we also entered and are still in the midst of a period of in which a precision experiment is beginning to deal with systems that behave quantum mechanically and on which you make repetitive measurements. And this is quantum non-demolition measurements. And through my contact with experimenters, Ron Drever, when he first came to Caltech, and we wrote our first paper on quantum non-demolition together with Carlton Caves and others. Through my close contact with experimenters, I've at least been able to think somewhat sensibly about this and to pass on a little bit of understanding of it to people in my own research group. So for me, although I was a theorist in an area where there was very little experimental contact, the process of bringing it into experimental contact was greatly benefited by having that understanding of the fundamental issues in high precision experiment. And so that's why I certainly encourage theorists to sit in on a course like this and to get exposed to the kinds of ideas we'll be dealing with. Also, from the point of view of the experimenters, we will be treating, to some degree from a theoretical point of view, a number of experimental issues, but the ability to model experiments is absolutely crucial, both in the design of experiments and in the planning and debugging of experiments, to be able to do mathematical modeling of experiments. And some of the tools that can be used for that will be treated in this course this term. I had an overview of the topics for this term, and I must have left it in my office. So I'll pass it out on Wednesday. So let me just give you verbally an overview of what we're planning to do. So, no, that's all right. That's all right. It's because it's going to be revised by Wednesday anyway. I'm still in the, so a number of the lectures will be given by guest lecturers, and I'm still working through the details of that. What we're going to do is initially treat idealized interferometers, and I'm going to do that this week, of the sort that are like simple versions of LIGO. Then we will treat real LIGO-type interferometers, and then we will move on to other types of gravitational wave detectors. Before doing LISA, space-based detectors, I want to do pulsar timing and Doppler tracking of spacecraft, in part in order to get a feeling for high stability oscillators, and which then play a role in LISA. And then we will talk about LISA and then about cosmic microwave background polarization as a means to search for gravitational waves. So I'm going to go through, we will go through various types of gravitational wave detectors, sort of one after another, but focusing on nearly the first half of the term on LIGO and physics underlying LIGO, because the physics underlying other types of detectors has a great deal of commonality with LIGO, and we need to get that physics in hand. There will be a number of guest lecturers as the term goes on. I haven't asked you yet, Ron, but I have you down for a lecture later on. I hope you're willing. And so I'll be doing maybe a third of the lecturing, and 2/3 will be done by experimenters who are working in this field from Caltech and from JPL. My goal is to teach some of the fundamental physics underlying this field, as well as to teach about the details of gravitational wave detectors, detection, how it's done, and data analysis. And on the problem sets, there will be a particular focus on the underlying physics. As the mechanics for the course will be the same as last term, with homeworks and a similar grading procedure, unless people object and want a different change. You let me know if you want any changes.
I just want to let you know that no one has failed last term, so...
Nobody failed last term, that's right. Okay, so any questions? Okay, so let me begin by discussing a idealized interferometer. And let me begin by motivating things by just talking about the problem of monitoring the motion between two test masses out in space that have some separation L, and the gravitational wave comes along and is going to perturb the separation in some time-dependent sort of a way. And just to put some numbers down that you're already familiar with, the gravitational wave strengths that we are interested in, and H is, aside from maybe a factor 2, depending on, aside from a factor of 2, H is delta L divided by L. Delta L divided by L is actually 1/2 H. And I'm not going to worry about that factor of 2 in this initial discussion. So the gravitational wave field strength, then, that we expect to be dealing with is of order 10 to the minus 22 in LIGO, a similar number in LISA. And in LIGO, we're going to have arm lengths of 4 kilometers. And I will typically use CGS units, so that's 4 times 10 to the 5 centimeters. Okay. And so our challenge is to measure then a delta L. Let me approximate that as 10 to the 6 centimeters for the purpose of the next few minutes. Our challenge then is to measure a delta L that is about 10 to the minus 22 times 10 to the 6 centimeters. So it's about 10 to the minus 16 centimeters, or about 1,000th of a Fermi. Where our challenge is to do that using light by bouncing laser light back and forth between these test masses. The light has some wavelength lambda sub e, and that wavelength lambda sub e is about 1 micron. 1 micron is the near infrared. It's in fact 1.06 microns for the laser, the neodymium YAG laser that's used in LIGO. So that's 1 micron is 10 to the minus 4 centimeters, 10 to the minus 6 meters. And so our challenge is to use light to measure changes in separation of test masses where the ratio of that separation to the wavelength of light that we are using is about 10 to the minus 16 by 10 to the minus 4, so that's about 10 to the minus 12. So Michelson, when he did his original interferometry experiment studying the speed of light, worked to some modest fraction of a wavelength of light. And today, 100 years later, one is trying to do things to something like part in 10 to the 12 better. And the issue is how can you do that? So let me turn then to the basic concept of an interferometer to do this. The basic idea is to take a laser, send out a light beam, send it through a beam splitter, send the light to some test mass up here, and to some test mass down there. The light goes down, comes back, it recombines at the beam splitter and goes out to a photodetector. So that's the crudest version of the idea. Now, when the gravitational wave comes along, it changes this arm length to, say, L plus delta L, that arm length to L minus delta L. Let's put this factor of 2 back in, okay? So H over 2 is delta L over L. And so delta L then is 1/2 HL. The light, in traveling down this distance L and back, acquires a phase shift, and there's a change in the phase shift due to the gravitational wave. And so that change in the phase shift, delta phi, is equal to the wave vector times 1/2 HL, but it goes down and then it comes back, and so you get twice as big a change in phase as you would get in just going down, so the factor of 1/2 goes away. So that's equal to K is 2 pi over the wavelength of light times L times H. And similarly on this arm, the light goes down, comes back, has a phase shift in the opposite direction. I'm assuming for simplicity the light is coming down from overhead or up from below, and so and we have the plus polarization so that you get equal changes of separation along this arm and along that arm. And so there's a phase shift on this arm that is equal and opposite. Delta phi is minus 2 pi over lambda E L times H. Now let's look at issues of the gravitational wave length. We're looking at gravitational waves that have a gravitational wave frequency that is of order 100 hertz for LIGO. And so it has a wavelength that is the frequency, or it's 1 over the frequency and the speed of light. And so that's about 3 times 10 to the 5th kilometers per second divided by 100 hertz. So that's about 300 or 3,000 kilometers for the wavelength of the light, of the gravitational waves that we're dealing with. Now, we can ask, how long would we like to make the interferometer arms? Well, ideally, it would be great if we could have the interferometer arms have a length of about, say, a quarter of a wavelength, so that the light in going down and coming back, that takes about a half of a gravity wave period, during which the arm length is lengthened. At the next half period, the arm length will be shortened. And so we don't want to store the light for that next half period. We would just like to stick the light in, store it for about down and back for about half of a gravity wave period, and then extract the signal. That would be the optimal sort of thing to do. And so optimally, we would like to have an arm length that is something like the wavelength of the gravity waves divided by 4, or something like 1,000 kilometers, ideally. That's not practical. When Ron and I and Ray Wax went out to look at sites, we found one site that might have supported a 50-kilometer interferometer, but 1,000 is a bit long, and we wound up with 4 kilometers for having practical sites. So this desired wavelength is quite a bit longer than the actual available, or the desired arm length is quite a bit longer than the actual available arm length. And so what we do then in order to deal with that, in order to optimize our interferometer, is to store the light in each arm for a time that corresponds to about half a gravity wave period. And there's 2 ways to do this. Basically, you want to bring the light in and you want to bounce it off of some mirror here and bounce it back and forth some number of times that corresponds to half a gravity wave period. There are 2 ways to do this. A way that Ray Weiss was pushing at MIT in the 1970s, where you bounce the light back and forth, making discrete spots on the mirrors. And this was called a Michelson interferometer. But the number of times you need to bounce, let's just see what that number of times you need to bounce is. Say the number of round trips that you want is about 1,000 kilometers for the desired arm length divided by the actual arm length, which is 4 kilometers, or that's about 250, let's say 200 round trips. That's what we would like. Now you can imagine if you want to make something like 200 discrete spots, sending the light down and back, making discrete spots on a mirror, that's going to take a terribly big mirror. And so while it's conceivable one might do it that way, it's not really awfully practical. And so Ron Drever invented an alternative technique where one would operate each arm as a Fabry-Perot cavity, so that you have these 200 light beams, well, 400, 200 going down and 200 coming back, that are superimposed on each other as a single beam. And so we're going to want to understand how that is done and the theory of such cavities. But the bottom line is then that you stick in another pair of test masses in here, one here and one there, and you use them, you coat them with mirror coatings on the inside faces and anti-reflection coating on the back face. So the light gets sucked right through, or it goes right through the back face with ease with this anti-reflection coating. And then it gets caught inside this optical cavity, bounces back and forth about 200 times, and then comes out. And that, by doing that, we can increase the phase shift then by a factor of b, where b is the average number of bounces. Now with a cavity, not all photons will bounce back and forth the same number of times. It'll be a statistical thing. And so b is basically some average number of bounces. So increase by a factor of b here, a factor of b there. And so now our challenge is made somewhat easier. We have built up then a phase shift. Let me do some numbers. We know to measure a phase shift between the two arms. That's the delta phi in the x arm minus the delta phi in the y arm. We have a phase shift that is 4 pi L over lambda E B times H. And our challenge is to measure that phase shift, or relative phase shift, between the two arms using interferometry. Let's look at what this is numerically. 4 pi is approximately 10. Our arm length was 4 kilometers. The wavelength of the light was about 10 to the minus 4 centimeters. Let me make that 4 kilometers be 4 times 10 to the 5 centimeters. B was about 200, and H was about 10 to the minus 22. Okay. So 4 times 2 is about 10. And then I have a 100 and a 10, so that's about 10 to the 4 that comes from these guys. And I have a 10 to the minus 4 down here. And I have a 10 to the 5. So 10 to the 4 and 5 is 9, and 4 is 13, times 10 to the minus 22 is about 10 to the minus 9. And so it's wonderful. Instead of having to measure, as I said before, a change in separation that's 10 to the minus 12 of the wavelength of light, we're dealing with measuring a phase shift that is only in quotes, about 10 to the minus 9 radians. We've picked up a factor of 4 pi, that's one of the 10s. And we've picked up a bounce factor, which is a factor of about 2 orders of magnitude. But we can't store the light any longer, or we can't store the signal in here any longer than about a half a gravity wave period. We no longer gain because, as I said, if the next half cycle of the gravity wave, the separation will change to the opposite sign, and so we would be putting on a phase shift of the opposite sign of what we put on before. So this is about as well as we can do with this kind of an interferometer. So the challenge then is to measure a phase difference in the light from the two arms at a level of 10 to the minus 9 radians. So the question is, how accurately can we actually do it? Well, first let me comment on how we do it. So the light comes back with this phase difference on it, produced by the gravitational wave, a phase difference that's going to oscillate in time with a frequency of roughly 100 hertz, because the gravity wave is oscillating at 100 hertz frequency. We want to turn that into something that we can measure with precision. And the precision kind of a device for measuring light is a photodetector. So we want to change a phase shift on light into the thing a photodetector measures, which is a light intensity, or a light power. And an interferometer does that. If we will go through the details of this, or you will on an exercise. If you bring the light in with a shift in the relative phase between these two beams, then at the beam splitter, that phase shift will cause a change in what fraction of the light goes toward the photodiode and what fraction goes toward the laser. And so as the gravity wave oscillates and these arm lengths increase and decrease, and you have an oscillating relative phase on the light beams coming back here, you wind up then with an oscillating fraction of the light going toward the photodiode, toward the photodetector. And so you can measure just directly the intensity, and the intensity reads out then directly the phase shift as a function of time, which is proportional to h as a function of time. So that's the basic idea. Now, I want to estimate the accuracy with which that can be done without going through the details of the optics and of the interferometry. I'm going to derive a variant of what Farid Khalili calls the energetic quantum limit. In order to make a measurement at a certain level of accuracy, you've got to have a light beam that has a certain amount of power in it. And so it really is, it's the amount of laser light you've got coming into here that will govern how accurately in an interferometer you can measure the phase shift of the light that is being recombined here and turned into an intensity. And so I'm going to derive an upper bound for a given amount of laser light, an upper bound on how accurately you can make a measurement. But it turns out that interferometers are really ideally suited to this, and they do achieve this upper bound. But you will verify that they achieve it in an exercise that I'll give you for this weekend, or I'll sketch the argument on Wednesday. So the upper bound, or the so-called energetic quantum limit, it comes from the energy-time uncertainty relation of quantum mechanics. You may recall that the energy-time uncertainty relation has a little different status in quantum mechanics than the position-momentum uncertainty relation. A little different status because time is a parameter in quantum mechanics. It is not an observable in the fundamental theory of quantum mechanics. And so you're dealing with energy, which is an observable, and time, which is a parameter, by contrast with the position-momentum uncertainty relation, where both things are observables. So there's a different status. But there's a lovely and rigorous version of the energy-time uncertainty relation due, I think, to Peierls and Landau, I think, was either in the early 30s or late 20s. And basically what it says is if you have a clock and you're measuring time by some oscillatory behavior of the clock, so it's, let's say, an atomic clock, or in our case, the clock is the oscillations of the light, as this very monochromatic light, the wave field oscillates. If you have a clock and you use that clock to measure time, and that clock also has some amount of energy in it, as you use it to measure time, then if you want to make a measurement to a certain level of accuracy for time, for the time interval, say, between two different events using this clock, and this is to be the level of accuracy, then you will be forced in your clock to have some uncertainty in how much energy it has. That uncertainty in the energy times the uncertainty in the time is greater than or of order h bar. And I forget in the rigorous version whether there's a factor 2 here or not. I'm not doing things at that level of accuracy. Pardon? Of your delta E. So this is the uncertainty in the energy. That's the uncertainty in the time measurement. You're probably familiar with this from atomic decay. If you have if you have an atom that is decaying, and delta T is the half-life, so it's the uncertainty in the time that it's going to take for the atom to decay, then this delta E is the width of the resonance associated with that atomic state, or the uncertainty in the energy of the state of the atom that's decaying. So that's familiar from there. The application that I want to make is to an incoming wave train. And there's some number of wavelengths in here. And what we're trying to do is basically measure the phase of the light, of this light as it oscillates away. So it's basically let's take the zero this, and so the zero crossing, the time of the zero crossing here is a time that we would like to know to some level of accuracy. And that time of zero crossing has some uncertainty delta t. And if I multiply by the angular frequency of the light times delta t, I get the uncertainty in the phase of that incoming wave train. And so this is how I'm going to relate it to the energy-time uncertainty relation. And then the issue is what we're trying to measure is a phase of the light, but we measure the phase by averaging over a long period of time. How long do we have to average? Well, the averaging we're really doing is we're sending a light signal into the photodiode. This is how we're going to make the measurement. And we're going to average the intensity over some length of time. The duration we have to average is basically half a gravity wave period. We want to know what the phase of the light is, averaged over about a half a gravity wave period. Okay. And so the total energy in this light beam, this is not the uncertainty in the energy, the total energy in the light beam is actually equal to the laser intensity, let me call it I naught, times a gravity, half a gravity wave period, so that's 1 over twice the frequency of the gravity waves. So that's about 1/200th of a second, since the frequency is 100 hertz. Okay. This is the total amount of energy. That's equal to h bar times some total number of photons that we have available to ourselves that come from the laser. This is the total number of photons we have actually available. Okay. To work with, and we want to use them as cleverly as we can. H bar times that total number of photons is the laser power times half a gravity wave period. Yeah.
H bar omega?
No, h bar omega times the total number of photons. Omega e times the total number of photons. Okay. Now, the light that comes out of a laser, if you work very hard, you get it into what's called a coherent state. So, coherent state light. And that's the standard form of light coming out of a very good laser. That coherent state light has a uncertainty in the number of photons that you would have available to you coming off of that laser that is equal to the square root of the number of photons. This is a property of a coherent state that I'm going to appeal to from quantum mechanics.
The number of photons is measured at a specific time.
So this is the number of photons over your averaging time. So I have my light, I've sent light in for 1/200th of a second. I'm averaging for 1/200th of a second in order to measure the phase of this light by averaging for 1/200th of a second. I have a certain number of photons, and delta n, the uncertainty in that number of photons, really due to the randomness in the Poisson distribution of the arrival times of the photons. That uncertainty is delta n.
So that's the uncertainty in the average, then, in the average number.
In the total number over some duration of time. So we have a total duration of time during which we're making a measurement. So it's the total, so n is the total number of photons in this piece of wave train that lasts for 1/200th of a second. N is the total number of photons in there. And delta n, square root of n, is the uncertainty in how many photons I have in there. And similarly, then, the uncertainty in the total energy that I have in my clock. My clock is this wave train that lasts for 1/200th of a second. The uncertainty in that energy is delta n photons times h bar omega e, or it's square root of n times h bar omega e. So to reiterate, the connection with the energy-time uncertainty relation is we're trying to measure a time, and the time is basically something like the average time of these zero crossings, or correspondingly we're trying to measure the phase of this light by averaging our signal over 1/200th of a second. Our clock is this wave train. This wave train has an energy given by this formula, and it has an uncertainty in the energy given by that formula. And I now want to apply the energy-time uncertainty relation to this clock. When I do that, then I see that delta t then, wherever it went, delta t times delta e is the phase shift, or is the accuracy of measuring the phase divided by omega e. Delta energy is the square root of the number of photons that I have in this 1/200th of a second train of light times h bar omega e. And this has to be greater than or approximately h bar. Okay. Is that clear? Okay. So my h bars cancel out, and this omega e cancels out against that omega e. And so the statement is that the accuracy with which you can measure the phase of the light in a wave train is no better than 1 over the square root of the number of photons that you have available for the measurement that you have in the wave train. And so this is the best you can do, and we will see on Wednesday or in the homework that in fact an interferometer actually achieves this very best accuracy. This is an energetic quantum limit in the sense that it says that in order to measure a phase at a given level of accuracy, and correspondingly then to measure a gravitational wave at a given level of accuracy, since the delta phi that we're trying to measure wherever it went, was the delta phi. It's these factors times h. And so we're trying to measure the phase shift. We're trying to measure h. Okay. So to achieve a certain level of accuracy on h, corresponding to a certain level of accuracy on the phase shift, we've got to have some minimum number of photons. And that number of photons, just inverting this, is we've got to have greater than or of order 1 over delta phi squared. The delta phi that we need to achieve to get to a 10 to the minus 22 in the gravity wave strength is 10 to the minus 9 squared. So we need 10 to the 18 photons to do the job. And if the experimenters are really clever, then they can do it with 10 to the 18 photons. But there's no way they can do better so long as they use coherent light. Now, later in the course, we'll talk about tricks of using light in non-coherent states in order to beat this energetic quantum limit by modest factors. But so long as you're using coherent light, this is a limit on how many photons you've got to use in order to measure a phase shift of a given size. Okay? So what does that correspond to in terms of laser power? The laser power, let me box this in. It's a number worth remembering. I always carry around this 10 to the 18. It's an impressive number. That's how many photons you've got to collect to get one data point, to get one good data point in LIGO. 10 to the 18 photons. So the total intensity of light that this corresponds to is the number of photons times the energy of each photon, h bar omega e, divided by the duration of this pulse, which is the gravity wave frequency, divided by 2. Okay. I'm sorry, that it's 1 over It's 1 over 2f. So that's n gamma h bar omega e times 2f. Well, it's straightforward to plug the numbers that we have into there. N gamma is 10 to the 18. Planck's constant by 2 pi is about 10 to the minus 27 in CGS units. The angular frequency of the light is about 2 times 10 to the 15 hertz for this 1 micron light. This 2f is 200 per second. And this I naught then works out to be approximately approximately 100 watts. Or 10 to the 9 ergs per second. So that's what we need basically for LIGO 1, for the first LIGO interferometers, is 100 watts of laser light. Okay. Is that number right, Alessandra? That's about right.
It's not very high.
Pardon?
It's not very high.
It's not terribly high for LIGO 1. You're accustomed to thinking about LIGO 2, where it's a rather higher number. In LIGO 2, we want to improve the phase shift measurement by about a factor of 15. So the number of photons goes up by 15 squared. So that's about a factor of 200. So in LIGO 2, we're talking about something like 20 kilowatts in LIGO 2. 100 watts in LIGO 1, 20 kilowatts in LIGO 2. Now, 100 watts still is a lot of laser power. And thinking about that back in the 1980s when we started to plan LIGO, we recognized that really one needed to use a trick to get that 100 watts of laser power. And so again, it was Ron Drever who proposed the trick. And the trick was to put another mirror in here. So I'm going to add one more mirror, which Ron called a power recycling mirror, so that the light would come in, go through this mirror and our reflection coating on the back, a reflective coating on the front, go through the mirror and go into the interferometer, bounce around about 200 times on average and come back, and you would operate the photodetector on the dark fringe so that very little of the light went toward the photodetector, most of it went back toward the laser. The light that went back toward the laser would get reflected back in. And if you adjusted the position of this mirror just right, it would reflect it back in phase with the incoming laser light. And so it would build up in the interferometer. And so on the exercises for this weekend, I'll let those of you who want to work out quantitatively a power recycling configuration like this. Yeah.
What happens with the phase shift due to gravitational waves or noise?
So as we will see when we analyze this, the phase shifted light, the piece of the light that carries the gravity wave information, all goes out toward the photodetector. The light that goes back toward the laser is not carrying the phase shift information. And it merely would just get lost normally. And so what Ron said was, let's recycle it back in with a power recycling mirror in phase with the incoming light. Okay. So this is another key property of an interferometer. The gravity wave signal goes out one port. The bulk of the laser light power goes back toward the photodetector. That's something that we will work out quantitatively. Okay. So this lecture today is just an overview of these things. Okay. And so I looked up in an ancient document what the numbers are for the planned LIGO 1. Alessandra or Ron may be able to tell me whether this is still true. But the laser power is at that time about 5 watts. But you needed to have 100 watts of light coming in here and to be usable by the interferometer. And so the recycling factor, the buildup, There's roughly 20 in order to get up to roughly 100 watts. Okay. Is that still the number that they use for LIGO 1?